So good morning, ladies and gentlemen. It's very nice to be here. I'd like to welcome you, as said, to our first talk of today. It's about AI and AI introduction. My name is Ole Dreessen, and Will Mitchell, actually from Anglia, is joining me in the second part of that talk. It will be roughly 30 minutes, and then we will have about 10 minutes for Q&A. But if there are any questions in between, please let me know. So, in the first place, I wanted to introduce you to AI. So what actually can AI do? And I brought a nice picture of the cat. And the exercise is like to distinguish is a cat to be seen in this picture or not. So that's a very common use case. Could be object detection, could be object classification, whatever. But in this exercise, we want to distinguish is there a cat present in the picture or not. So actually, in the traditional software ways, it's really hard to do, because you would like to use if-then-else clauses, which are rule-based, and describe a set of rules, like for, in this case, looking on the noses, on the whiskers, or on the triangular ears, and stuff like that. So these are features which you just check in that picture. The problem with that is that this is a nice picture of a cat, but actually I brought some others. We could have a picture of a cat which is shown from the back, or just partially, or maybe the cat has had an accident or something. So it's the traditional features may not present in the picture. So what you have to do then is you have to write code with lots of exceptions for that. And this can be hundreds or thousands of exceptions, right? So actually, what AI is doing is like we are forming an AI network, and we are feeding this cat image into that network. And the outcome of that network will be, I'm not quite sure, but I'm 98% sure that's a cat in the picture. So that's the first difference between a traditional software approach from an if-then-else clause, where the result's quite clear, rather than the result of an artificial intelligence, which says this is a predicted stuff. Okay, so it's not 100%, it's just 70%, or it's 98% or something. So talking about the network, it works like you train that network in the first place, showing hundreds of thousands, maybe millions of different cat pictures to that network. And then if you put that network into production, it can distinguish a cat from a horse or a bike or something just from a freshly taken picture. So it's not necessary that the picture you want to run through that network later on has to be in that bucket of the millions of training pictures. So yeah, that's it. So actually, what's a neural network, or what's a neuron? So everything starts actually with a neuron. A neuron is like its biological pendant. It has a couple of inputs and one output, and it's nothing else than linear algebra, right? So we do have boxes in that neuron with weights and biases, and literally the input is multiplied with the weight, and the biases are added to that value, and the intermediate values here are just summed up. So that's the input or the internals of a neuron. And then we got an AF, which is an activation function, And that's actually because we want the neuron only to be fired if the input here is meaningful to that neuron, right? So, and there are different activation functions which are available. For instance, there is a rectified linear unit, sigmoid, and many, many others. It's not really relevant to us for the moment. We at Analog Devices use rectified linear unit in our hardware accelerator because it's very, very easy to do in hardware. And the function is like if the input value is 0 or below, the output is 0. And if the input is above 0, the output stays the same then. So that's called ReLU or rectified linear unit. So actually this is a neuron now, and a network consists of many, many different neurons, and all these neurons are like sorted into layers. So we do have different layers. The first is always called input layer. Then we have one or multiple hidden layers in between. And the last one, the output layer, is the output layer. Is in this case, this layer is representing the different classes we want to distinguish. We see that in a bit. Yes. So actually, this is a full operational network, which is called CFAR or CFAR 10. The 10 in this case stands for 10 different classes which you can distinguish from, and you can see that here. So this went over there, and here is the output values: cat, dog, tiger, horses, whatever you want to distinguish from. And if you put that into production, you're just running your captured sensor image through the network, and in this case, it gets the distinguishable features like the whiskers we talked before, or the noses in these feature maps, and they are transported through that network. And here at the very end, the probability scores are formed. Okay. So, Will, I think it's up to you now. So,
thank you. Hi there. My name is Will Mitchell. I'm from Anglia. I'm obviously presenting with Ole. Ole's briefly covered what AI is and how it works. What I'd like to do is kind of reference that now to what the benefits of AI at the edge are, so taking a look at what actually is edge AI, what are the performance improvements we see with specific AI MCUs, and then I'll cover a couple of standard applications that we might see or you might already see, as well as a specific use case that has been done at Analog Devices and can highlight the benefits of using an AI network. So AI at the edge, what does it mean? It's terms that we hear a lot at the moment being bandied around. Edge AI is kind of a compound buzzword that is used a lot. Typical computer systems, when they were kind of brought to life, were very centralized. And as tasks and operations were then made more external and passed to external terminals to be able to function, they then became able to perform these without the interaction of another computer, and we saw edge operation. Now, with the invention of the internet and the usage that we all have these days, we're much more reliant on a centralized system, and if we come back to using the cloud, I think we all use that probably in our personal and work-based life, and we all know once that goes down, nothing really works properly. So what we see with AI at the edge or intelligent edge is the opportunity to perform tasks and operations which aren't necessarily reliant on internet access, which is kind of a limiting factor sometimes for these scenarios. So some of the system performance and the benefits that we see for AI at the edge, and specifically AI MCUs. Energy saving, the hardware accelerator that's built into the, as Ole has mentioned, the AI MCU allows for greater concurrency and running of operations at the same time, and because of that we also see a reduced instruction set for the MCU, allowing for efficient operation. Lower bandwidths, the decision to make kind of making edge apologies, load bandwidth, being able to perform operations at the edge and be able to make those decisions allow for a lower transmission of data. Typically, these kind of edge sensors are capturing huge amounts of data, and the transmission rate is maybe happening once every minute, once every hour, or maybe once every day to preserve the energy consumption, especially in RF applications where the power consumption is a lot higher. By being able to make the decision at the edge, we're able to save on energy and send only the decision data back to the centralized hub. Latency reduction, obviously very key for certain applications. Maybe we see in self-driven cars where we don't need a delay in the decision to steer left or right. And even for Face ID, remote safety critical sites, having that faster inference time allows for a lot less delay on any kind of operation, and even having to transmit the data back to the cloud causes delays for any kind of operation. And then, kind of as I've already highlighted, powerful decision making, be able to operate and make decisions at the edge, limiting kind of the amount of reliance we have on the central system. And then also I'll go on to talk about advanced pattern recognition and using healthy data to be able to train the models that we use today. So I'm sure we'll value some numbers. This is a comparison that was done at AD, comparing the MAX 78000, their first AI MCU, the MAX 32650, which is one of their ultra-low power MCUs meant for big applications, but running off small batteries and low consumption, and a undisclosed competitor part that was labelled as a low power option. And what we can see along the bottom is we have the two different operations. We have the keyword spotting and Face ID. And for the MAX 78000, for both against the MAX 32650 and also the competitor, we see them outperform them considerably, not only in latency, but also in the power consumed to perform the inference. So these give an idea of the power savings that we can have. And this is through the implementation of the convolutional neural network on the hardware accelerator that's embedded in the AI MCU. And whilst the standard MCUs might have increased flexibility for our designs, a lot more control over how the operations you can do, you then pay with that in the increased latency and increased consumption, which for edge applications is becoming more and more of an issue. So I'm going to quickly run through some very basic applications, ones that you might see already with customers, some that you will see probably in your own homes, and kind of briefly cover what options you could do to integrate AI into those. So a typical security camera, face recognition, it's very easy to put in. People counting for maybe large events. We're seeing huge swathes of people coming through London for the music events, for sporting events. Multiple people counting could be important for managing the control and flow of a crowd. And something we were discussing only yesterday, object detection. Standard solutions implemented may be erroneous when something moves within the frame. So whether that's an animal, a branch, could be anything that is then flagged as a potential error or issue, when the AI MCU will be able to classify that as a person and only flag that if it's actually an issue. Drive-through systems, goods in, multi-keyword spotting has already been mentioned, being able to have complex command comprehension without a human sat at the other end. Audio quality, at the moment a lot of us I'm sure have the active noise cancelling headphones which are currently running on DSPs. Integrating the AI MCUs would allow for greater battery life and increased performance with the low latency that it provides. And of course, the object detection could be integrated into this if it was something needed for the goods in applications. Robot vacuums, I'm sure a few of you have them roaming around your homes. If you could use this as a command, if you've got guests over and you could tell it to dock, you can use the keyword spotting. Object detection, whether this is for your home, if you've got children or dogs running around, or in an industrial setting where you've got other robot vehicles operating, you can use that to actively avoid them. Or maybe something a bit more specific in sound classification. If you're looking for, in a goods in area, you're looking for potential damage that could be caused to your goods coming in, or in a home, if it's smashed glass or the sound of something breaking, that can alert you and just provide that slightly smarter information in your home. I'm wearing one. I'm a sucker for wearables, but and we're seeing more and more Bluetooth control or remote control of music. But this can be adapted and used for keyword operation, voice ID unlock for a unique user. Again, the audio quality, something that we can maybe include on watches with the lower power that the AI offers. And also, we're seeing more and more health sensors being integrated on devices from Garmin, Apple, even looking for FDA approval. And with smarter algorithms that could be run on these devices, it kind of opens up the field for more and more options. Now, a very brief use case. Trying to think. Yes, because I'm running. Global energy typically is consumed, about 30% of it is the industrial sector, with, as the stats are saying on here, 69 of that consumed by electrical motors. Some of these motors perform poorly, whether that's from the setup, whether that's from the materials used, and all of this is causing and resulting in mechanical vibration issues, something that we can measure with sensors. I think today we've got our Voyager 4 on the Anglia analog devices stand if you'd like to come and have a look. So the common kind of issues, the mechanical faults, you have misalignment, excessive vibration, causing deterioration of the components you're using, bearing faults, something that may not be in the setup, but actually the components you're using and might help influence the selection of these components, and imbalances that could cause early failure of the equipment. Again, all of this is resulting in vibration that we can detect using the motion sensors. So Ole talked earlier about having access to data such being able to load into the networks the healthy data, normal data. So if you're looking for cats, you can load loads of images of cats and train the models to be able to recognize it. In industrial settings, this isn't always possible. You're not always going to have accessible data that you can download and train these models on for every fault possible. So standard machine supervised learning isn't a solution here. What we can use is healthy data from already operating systems that are functioning and operating as they should be. And the Edge AI system has everything needed to be able to train this. And what we can do, instead of training it to recognize something, we can train the systems to recognize a deviation away from normal, healthy operation. So in this example, it was trained with healthy data. We have the training data that's used at the top to set the threshold of just above 0.116. We've got the validation to make sure the model has been trained correctly, and then the reconstruction error with faulty data shows, you can see the new threshold, or the threshold set by our training data up here is then able to identify the anomalous data that is then outputted by the tests that will run on our motor. So the results this was simulated with 12 faults, 5 speeds, and 2 loads. The initial results came back with about 90% accuracy. I think the team then thought, can we make this better? So the information from the vibration sensor was passed through normalized distribution, which was then enabled increased fault catching. And then it's thought, well, this is going to be potentially an edge application. Can we make it more efficient, and can we make it faster? So it was then put into a spectrogram CNN, which then approximated the data that had been put into a spectrogram, and was able to operate at a higher efficiency and higher accuracy, which with this system was able to catch 99% of the faults. And I think I'll pass it back over to you, Ole.
So, I'd like you to briefly introduce you to our parts, which you recently got. So this is the Max 70000 family. It's on the first side. It's a standard ARM Cortex M4F microcontroller. So the left part of that block schematics is just an ordinary MCU. It's equipped with standard flash, etc., pp, all the peripherals you would need. For instance, EPC CSI2 camera interface. And the magic starts here on the right-hand side. This is our own IP, which we developed a couple of years ago. It's based on it's actually a CNN accelerator using 64 processing nodes in parallel. And the trick is to not move data, specifically the kernel memories as well as the weights and biases, not around the external flash. So we put literally direct memory here in that processing structure, such that you do not have to move any of those datas for the inferences from A to B. And this is actually the reason why we're saving so much energy, and the latency goes down as well. So it's equipped with so this device is the MAX 78002. It's equipped with 2 megabytes of kernel memory, and with using these 64 processing nodes, you can run convolutional neural networks from a I mean, it's 128 layers in size approximately. So these are the limits. And as we'll just mention, the use cases are one-dimensional and two-dimensional data pattern recognition approaches or applications. So we provide typically EV kits and reference designs for our parts. So these are the two bigger ones, EV kits. This is the Max RefDes. So that's a total complete reference design. We put a VGA camera in the front, an LCD screen on the rear, and you can actually run any sorts of network, which is, for instance, vision-based, and can display the results directly on the LCD screen. It's quite handy for instance, collecting training data as well. Okay, so I brought one slide about the developing flow for that devices. As you may be aware, these two open source tools, PyTorch and TensorFlow. So that's what we use as well. We provide you with a hardware-aware module, which just represents the capabilities which can be done in our hardware. And then what you actually do is you put in your training and test data set, and then you start the quantized aware training. And the outcome of that will be either a checkpoint file or an Onyx file. So this is everything which is in here is open source. And the last layer is the synthesis layer here, where the result will be an embedded C code. So actually you get header and C files out of here, which holds the network structure, all the weights and the kernel memories, and you take that and include that in your standard MCU environment like Eclipse, Kyle, IRR, or whatever you want to use. And that's done the development flow. Okay. So now I would say that's literally the end of the talk. It's about time for Q&A session. I think we have still no, it's 10 minutes or so. So are there? Oh yeah, sorry. Are there any questions? Oh yeah, yes, please.
Down here at the front.
Hello. So when you presented the adversarial encoder, I didn't exactly understand what was happening there. Is the adversarial part just the encoder that was fitted on a Gaussian distribution? Or
Sorry, say that again?
For the adversarial encoder, I didn't understand. Was that just a Gaussian distribution that got fitted over the data set, or?
Yeah. So there was it was fitted over the data set so that the fault data wouldn't be registered as healthy data. So it would measure the separation from healthy data, and anything that was considered erroneous wouldn't be registered in the training as something that was healthy.
I see. And then that got fed into
and then it was fed back into the network.
Did you take into account, I've seen NVIDIA do something similar for their guns, where basically you could have missing data points, for example, and you want to fit, instead of using a distribution and fitting a distribution over, you can use another neural network to kind of better fit a distribution so you don't have any holes in your approximation.
I think this is something that the AD team were doing. This one was done, I want to say, it was quite a while ago.
Yeah,
it was very early on.
Yeah.
The team put it together. So I think there's still tests running for the latest Mac 78002.
Sure.
But I don't know. I don't know if they've done something similar, but I don't think that was considered in this this test.
Okay, thank you.
Any more questions? So, any more questions? No? Yeah, those.
Hello. I wasn't sure why there was a RISC-V core in there.
Yes. Give me a sec. So yeah. So the, actually, this is a dual core MCU part, which is the so this actually is the ARM core, and we do have included a RISC-V core as well. The main purpose of that is that you can use, for instance, the RISC-V core for moving image data into the CNN structure, pulling out the results afterwards, without utilizing the ARM core. So you can put the ARM core to sleep during that time.
It's not symmetric multiprocessing, is it?
No, it's not.
Okay.
No.
Thank you.
Okay.
If anyone thinks of any other questions afterwards, we'll leave our emails on the slides. And if anyone's been at the back of the room, there are a few more bags, gift bags at the front. Please feel free to collect them. And there's also a QR code that you can scan for the presentation material to be able to enter our competition for some of the Max RefDes 178 cubes, which are going to be shown on the stand today, which Ole will happily run you through.
This is this actually.
That one. And we'll also be running some AI MCU workshops either later this year or early next year, which if you scan the QR, you can get early notification for, if that's something of interest. But otherwise, thank you very much for coming and enjoy the rest of your day.